All right, my friends, welcome to part 2 of section 11.3, the tangent line problem. Let's go ahead and do one example that practices what we did in the last lesson, in the last part, and then we'll move into something a little different. So for example 3, part A, let's have you find the equation of the tangent line to the graph of f of x equaling negative x squared plus 2x plus 3 when x equals negative 1. Okay, super good time to see if you can do this from memory and then check in with me. So for this problem, first I would recommend you use good notation to find the slope of the tangent line at x equals negative 1. So think about what that would be, f prime of negative 1. Following the definition of the derivative of f at the point where x is negative 1, you'd have the limit as x approaches negative 1 of f of x, which in this case is x squared plus 2x plus 3, minus f of negative 1, all over x minus negative 1. A note, since they didn't tell you what the y-coordinate is, you can just figure it out yourself by plugging it in. And then evaluating it, and it looks like f of negative 1 is 0. Okay, so from here then you'd have the limit as x approaches negative 1 of just negative x squared plus 2x plus 3, and f of negative 1 is 0, so on the bottom you just have x plus 1. If you try to evaluate this, you'll have 0 over 0, so let's use the factor and cancel technique. I like always factoring the leading coefficient out, or the negative leading coefficient out if in factoring. Let's see, let's do x minus 3, x plus 1, 2. There we go, all right. So canceling the common factor there, and then I'm just going to let x, all the remaining x values attain the target value. So if x attains a value of negative 1, I'd have negative 1 minus 3, negative 4, but then that's being reversed, so I'd get 4. So according to my work, the slope of the tangent line to the graph of f at negative 1 is 4. Now, why am I not done yet? Because they didn't say the slope of the tangent line, they said the equation of the tangent line. So now I just need to figure out what would the equation of this line be. So I've got the slope, and wouldn't it be nice if I had a point that's on the line? Well, I do, because right here I would know that negative 1, 0 is what's called my point of tangency. So it's a point that's on the graph of f and the line graph in my tangent line graph at the same time. So I'm just going to pull these two things together using point slope. So I would have y minus 0 equals my slope times x minus negative 1, or x plus 1, and I'm done. You are welcome to simplify that if that y minus 0 is going to ruin your day, but you could also just leave it like that. All right, so that is it for part A. Now for part B, I'm going to ask you to graph what just happened. So let's show a picture that shows the significance of what we just found. So what that means, when I say this, what I mean is graph the original function f. So let's get started on that. You know, we've got different ways to graph parabolas, but I'm going to complete this square. I'm going to group the x's and factor out the negative there. I'm going to kick the constant term out. divide your linear coefficient by 2, square the result. So the magic ingredient here is 1. It looks like I added 1, I actually subtracted 1. So to balance that, I'm going to add 1 onto the same side of the equation. So I just added a fancy version of 0. And so now I'd have the opposite of x minus 1 squared plus 4. So now let's go ahead and graph this guy. So the vertex is at 1, 4, it opens downward. From here to the left 1 down 1, to the right 1 down 1, to the left 2 down 4, and to the right 2 down 4. Filling it in. There we go. Okay, now that's not all that we're going to graph. We're also going to add the equation of this line graph here. So we had found early on that the point of tangency was at -1, 0. And then we also found that the slope of the tangent line was 4. So from here, if I was to go up 1, 2, 3, 4, and over 1, and fill that in, I should have a line that appears to be tangent to the graph, as in it would intersect at the point of tangency, but it would not cross the original function anywhere in a small neighborhood around that point. And it also represents kind of the slope, whoops, oh my goodness. It also represents the slope of the graph at that point. There we go. Okay, and that, my friends, is what I mean if I say graph what just happened. All right, my friends, let's move into the second piece that goes with this lesson. So, example 4. Let's say I ask you, if I say given f of x equals x cubed, evaluate the following. Okay, and let's say for part A, I ask you to evaluate f prime of -2. Okay, so you go ahead and see what you'll do with that. Okay, and then assuming that you've done what you can, let's see what we'll do. I hope that you are using the definition of the derivative at a point from memory, my friends. It matters. Okay, so f prime of -2 is equal to the limit as x approaches your target number of -2 of f of x, which in this case is x cubed, minus f of -2, which would be -8, all over x minus -2. Also known as the limit as x approaches -2 of x cubed plus 8 all over x plus 2. All right, now evaluating this limit expression, if I was to use direct substitution, I'd get, guess what, 0 over 0. So we're gonna have to use the factor and cancel method. If you know the pattern for factoring in sum of 2 cubes, then good for you. I think we had 1 or 2 people in class that knew how to do that. And so if you are like me, and for the life of you, you can't remember that, so if you're kind of a slob like me, then what you're gonna do is you're gonna hope that x plus 2 is one of the factors. I hope that makes sense. So here's what I'm gonna do. I'm just gonna take this in good faith, because I'm like, hey, look, like I kind of need the x plus 2 to cancel out. So, and plus I know x plus 2 is one of the factors, because if I plug -2 in for x, I get 0 on the top, right? So I know x plus 2 is one of the factors. And then we just need to know what the other piece is, and we can just use synthetic division to get it. So synthetic for x plus 2 is -2. Synthetic for x cubed plus 8 is 1 x cubed, 0 x squared, 0 x's, and 8 ones. Drop, multiply, add, multiply, add, multiply, add, and you get your remainder of 0. And interpret 1 -2 4. as your other factor. And your x plus 2's cancel. Bye-bye indeterminate form. Let all the remaining x values attain a value of -2. So we'd have 4 plus 4 plus 4. I think that's 12. Okay, so we'd end up with f prime of -2 is 12. Now, graphically speaking, does that make sense? Like if you think about the graph of x cubed, and then you think about all the way over when you're plugging in -2, so you're at, what would that be? The point -2, -8. Does it make sense that your line would be super steep, like an up 12 over 1 situation? It should make sense when you're done. It should be kind of visually pleasing in that picture that's in your mind's eye. Okay, so let's say, so imagine, that's how much work that took, and then let's say for part B, I'm not gonna make you do this, but let's say I did. Let's say for part B, I was like, hey, well, what's f prime of -1? And for part C, what's f prime of 0? And for part D, what's f prime of 1/2? And for part E, what's f prime of 3? So let's say, same function rule, and I just want you to do all sorts of derivatives at certain points. Knowing how much work it was to do part A, how many of us are just super excited about doing that very repetitive work 1, 2, 3, potentially 4 more times? I think very few of us. So luckily, there is another way to get these answers. It's a little more work up front, but it ends up being very, very nice when you have to do a lot of different derivatives. It ends up saving a ton of time. So anyway, so in this case, it would cut your work down probably by about 1/5 of what it would have been had you done all of this. So let's talk about what's called the general, and then we can come back and do this. It's going to be easy peasy. Let's move into conceptually talking about the general form of the derivative. So the general form, what we're going to get is a function rule that you can plug in x values to, and it'll give you the slope of the tangent line at any x value that you want. So it's kind of nice. And so let's talk about the story. How did it come about? So we'll draw a picture a lot like the one we drew when we talked about the slope of a tangent line at a given point. So go ahead and draw, some given function f. We'll keep it nice and generic so it could work for any function f. And then basically what we're going to want is like the slope of a tangent line at, so last time we wanted f prime of a, this time we want f prime of x. So this time we're looking for, let's say something like that. We're looking for f prime of x. Okay, so let me just kind of make my intention clear. We want a formula for f prime of x. So no more f prime of a business for us, okay? Now, not to say f prime of a isn't important. It is, it has its place. But I'll tell you, when you get into calculus, it's pretty much all about f prime of x. 99% of the time, it's f prime of x. So let's make sure that you're comfortable with the story here, okay? So just like last time, we're going to say, well, hey, we know that f prime means the slope of a tangent line, and we know that in order to get slope, you actually need 2 points to get it, okay? So what we're going to do is so we want to know what f prime of x is, right? So we're going to go down the number line a little ways, and the distance that we're going to go is going to be called h. And so a couple of questions for you, okay? So if this is x and we went down the number line h units, then what's the value of this place on the x-axis? It would be x plus h. I hope that's what you were thinking. Next question, what are the coordinates of this point right here? What's the x coordinate? It's x, good. And then what would you do to get its y coordinate? Well, you take whatever your rule is for f and you plug x into it. So it's f, that point has coordinates x, f of x. Now let's go down here. Pretend that looks really straight, okay? All right, what are the coordinates of this point right here? Well, the x coordinate is x plus h, and the y coordinate is whatever you get when you plug x plus h into your function. So those are the coordinates there. So let's talk about first the slope of a secant line, which is not ultimately what we want, but that's okay. So the slope of a secant line. So what would the slope of this blue line here be? So the slope of a secant line. What would it be? Algebra 1, it would be f of the quantity x plus h minus f of x. So there's your rise all over your run, which would be x plus h minus x. There we go. And then notice that you could simplify the denominator, and this is going to be a big aha moment for some of you, just so you know. So the slope of the secant line would be, and actually, yeah, so it would be f of x plus h minus f of x. And how does that denominator simplify? That's right, it's h. So for anybody that's been wondering over the years, where did they come up with this difference quotient garbage? You're about to be very enlightened. Okay, so this would be a formula for the slope of a secant line, but we don't really want the slope of a secant line. We want the slope of a tangent line. So, so fun stuff. You need two distinct points to use the slope formula, but we still want the slope of this tangent line. So what's the trick? The trick is that we're gonna let this x value, or this point, creep along on the curve and get closer and closer to this point of tangency. So how close do we need these 2 points to be together? So that technically we can use the slope formula, but we can also get the slope of the tangent line. So the answer, my friends, is this point is going to have to move how close to this point? The answer is infinitely close. You can't have it be right on top of the other point, because if you did, you'd have no rise and no run. But if you get it infinitely close, then you could have an teeny rise and an teeny run, and then you could end up with something that is the slope of the tangent line. So to do that, we're going to have to move this guy right here. How close to x? That's right, infinitely close. So that when we plug that into the function and we do the slope formula on it, you'll get that slope of the tangent line that we really want. So with that said, if you want to go from slope of the secant to slope of the tangent line, you're going to still do f of the quantity x plus h minus f of x all over h. You're just going to need to write something right here. And let's talk about what you could write. Right here, you could write, the limit as x plus h approaches x. And I bet some folks were thinking of it that way, and that's exactly what is going to happen. But we would not be happy with this when it comes to actually executing the work. So there's another way of saying this exact same thing. If you want x plus h to get infinitely close to x, what do you want to happen to this distance in between the x coordinates? What do you want to happen to h? And so limit as x plus h approaches x is equivalent to saying the limit as h approaches 0. Dun, dun, dun. All right, so I'm going to take this little box here out, and we are going to write, to turn the slope of a secant line into the slope of a tangent line, we're going to write the limit as h approaches 0. There. And then in addition to that notation, you're getting a formula, just like I said in the beginning, you're getting a formula for f prime at any x value. So the notation that we use in this case for the general derivative is f prime of x. And it's the limit as h goes to 0 of f of the quantity x plus h minus f of x all over h. Okay, and so this is, so let's see, this is called the general derivative of a given function f, and then also known as f prime of x. That's its nickname. There you go. And what is it? It's a formula for the slope of a tangent line at any given function x. Okay, and it's okay if you're a little confused as to what on earth we're going to do with this. Let's show you an example to help you see what we're doing with this. So, example 5. Let's have you find the general derivative for f of x equaling x cubed. And we're going to use this limit process that you see here. Okay, feel free to pause the video and do it on your own if you feel like you know what to do. Before you go through this with me, at the very least, do your best to memorize this. Notice the two derivative rules, f prime of a and f prime of x, very, very similar. So it's going to take you some work to make sure that you've got them both memorized and you don't do that hybrid thing that people do where they have half this one and half the other one mishmashed, and then that always ends up being a big mess. Okay, so let's get started. We basically, if you're asked for the general derivative, they're asking you to find f prime of x, which is a rule that you can use to get slopes at different x values. So it would equal the limit as h approaches 0. Now, f of x plus h would be the quantity x plus h cubed minus f of x is x cubed all over h. Okay. Notice if I let the h's go to 0 right now, I'd get an indeterminate form, which means we have more work to do. Which means we need to figure out what x plus h cubed is, and I hope you remember your Pascal's triangle stuff so that you don't have to do this kind of by distribution process. So we would end up with the limit as h approaches 0. Remember the coefficients for a cube would be 1, 3, 3, 1. So we're going to have 1x cubed times h to the 0 plus 3x squared times h plus 3x h squared plus h cubed. That would be the expansion here. Remember the coefficients 1, 3, 3, 1 that came from Pascal's triangle. Powers of x start with the power that you had on the binomial and decrease by 1. Powers on h start at 0 and increase by 1 until you get up to the power that you're expanding it to. Okay, so minus the x cubed there, all over h. All right, notice that the x cubes vanish and everything else in the numerator has h as a factor. So we'd end up with the limit as h approaches 0. I'm going to factor that h out there on the top. So we'd have 3x squared plus 3xh plus h squared all over h. And bye-bye indeterminate form. And then if you let the remaining h's go to 0, let's see what we get. We'd have 3x squared, but then 3x times 0 plus 0 squared, all this stuff would go to 0, which means your rule, your general derivative of f in this case is 3x squared. All right, now let's talk about why this is so fantastic. Remember example 4? let's talk about part A. See how we got for f prime of this f of x was x cubed, just like it was with example 5. And we got f of negative 2 to be 12 by using the definition of derivative at a point. Well, what if we had done example 5 and we found out that, hey, the rule for the slope of a tangent line at any x value is 3 times your x value squared. So let's check and see, according to this, what would f prime of negative 2 have been? Well, it would have been 3 times negative 2 squared. And dun dun, does that equal? Surprise, surprise, it equals 12. So what would f prime of negative 1 be according to your general derivative? It would have been 3 times negative 1 squared. Notice this is a slope formula as long as your original function is x cubed. So this is the slope formula for your tangent line to the graph of x cubed. So simplify this and you end up with 3, which is what we would have gotten had we used the definition of derivative at a point, but I think it's way faster. F prime of 0 would have been 3 times 0 squared. And yes, these are things that you can do in your head. You wouldn't have to write that down. F prime of 1/2 would be 3 times 1/2 squared. F prime of 3 would have been 3 times 3 squared. There we go. So hopefully you can see what the general derivative gives you. It gives you a slope formula for a given function, and then and hopefully you can see how to use it. All right, my friends, we'll give you one more example just to make sure you're good. Example 6. Find the derivative of each function. Part A, let's give you f of x equaling x to the 4th plus 18. Now, a comment, when they say find the derivative and they don't ask for it at any certain point, the word general is implied. So they are asking you for f prime of x. All right, my friends, go ahead and see how this one treats you, just using the limit process. And then we'll go through it together. So f prime of x will equal the limit as h approaches 0. F of the quantity x plus h would be x plus h to the 4th plus 18. And then you're supposed to subtract off f of x, which is x to the 4th minus 18. Notice the grouping symbols to make sure you're subtracting the entire f of x statement. And then it's all over h. All right, do these from memory, my friends. Okay, so now you've got the limit as h approaches 0 of, and then use Pascal's triangle. The coefficients would be 1, 4, 6, 4, 1. So this would be the expansion of the x plus h to the 4th and then plus 18. Now I'm going to distribute the negative here. So I'd have minus x to the 4th plus 18. And it's all over h. All right, let's look for things to vanish. If things are going well with these problems, which it looks like, are they going well for me? They are not. Okay, I have a mistake. And here's how I know. If things are going well, then anything that doesn't have an h in it in your numerator should vanish. And see how my 18s, they're not going to add to 0. So I can see now I've got a mistake here. That should have been a plus, which means this should have been a minus. Okay, there we go. All right, now these will vanish. The x to the 4ths vanish. And notice everything else in the numerator has an h in it. And so the next step, I like to show factoring the h out. So h times 4x cubed plus 6x squared h plus 4x h squared plus h cubed all over h. Bye-bye indeterminate form. Let's let the remaining h's go to 0. So 4x cubed would still be there, but any term that has an h as a factor would go to 0. So our answer for the general derivative here is f prime of x would be 4x cubed. There we go. All right, my friends. One more just to make sure you've got it. Oops, sorry about the bonk there. Okay, part B. F of x is equal to 3 over the quantity x plus 2. Okay, go ahead and see what you can do on your own. This is a little bit of a challenge problem, so it would feel super good, I think, to get it on your own or mostly get it on your own. Okay, so f prime of x, starting by applying the general derivative rule, would be the limit as h approaches 0 of f of the quantity x plus h would be 3 over x plus h plus 2 minus f of x in this problem is 3 over x plus 2, and it's all over h. Okay. Next, if you try to let h go to 0 here, you'll get 0 over 0. So you're going to go back to your techniques for evaluating limits, and this one would fall under the category of simplify. So we're going to clean up this big old compound fraction. So that means this fraction, to get common denominator up here, would need to get multiplied by this creative version of 1. And 3 over x plus 2 would need to get multiplied by this creative version of 1. And it's all over h. Okay. Now from here, we'd have the limit as h approaches 0. Make sure you're writing the limit statements. And then hopefully this makes sense to you, my friends. We are going to distribute on the top. So I'd have 3x plus 6. And then I'm also going to distribute the negative 3 here. So I'd have minus 3x minus 3h minus 6. And then it's all over, you'd have common denominator. And I hope it makes sense that while you could expand these out, it really doesn't benefit you to do so. And then this entire fraction is divided by h, which is just like multiplying by 1 over h. Just a little flip and multiply type stuff there. Okay, so now we'd have the limit as h approaches 0. And notice that if you simplify this, the 6's vanish, the 3x's vanish, and you just have negative 3h on the top, and that h would cancel with this h. And little ones would be left in their place. So what would we have then after all that mess? So we'd have negative 3 on the top, and then on the bottom, we'd have x plus h plus 2 times x plus 2. And it's once you cancel the h's that you probably got rid of your indeterminate form problem that you had at one time. So let's see what happens when we let the remaining h's go to 0. We'd have negative 3 over this, if your h was 0, would just say x plus 2. And then you're multiplying by another x plus 2. So you could think of it as x plus 2 quantity squared. Bring down your prompt that this is f prime of x. And you found the general derivative of f of x equals 3 over x plus 2 to be negative 3 over the quantity x plus 2 squared. All right, my friends, I hope this is making sense. This is kind of crazy stuff, and this is all conceptual calculus. So hopefully things are going well for you, and hopefully you'll contact me if you have any questions. Take care, everybody.